Hi everyone, I'm Jeremy Daly. Thank you so much for having me at the Sri Lanka AWS Community Day. Today we are going to talk about how to fail with serverless. This isn't a failure story. This is when our applications are met with some sort of failure, how we can deal with those using the serverless services that AWS has for us. So as I said, my name is Jeremy Daly. I am an independent consultant and I am working with companies building in the cloud, mostly on serverless stuff. I've been doing this for a very, very long time. I started working with AWS very early on and then started using Lambda as soon as it became GA. I also blog, do some OSS work, and speak. I publish the Off by None newsletter every Tuesday that has all of the roundups of all of the articles for serverless news across the world. And I also am the host of a podcast called the Serverless Chats Podcast and a new Serverless Spotlight web series that will be launching soon. All right, I am also a Serverless Hero, which is a great program that AWS has that allows us to look at stuff early and give our feedback and really help promote stuff within the community. So our agenda is very, very busy today, and we only have about 40 minutes. So we are going to talk about distributed systems and serverless. We're going to talk about writing code for the cloud. We're going to talk about the failure modes of the cloud. We're going to talk about some serverless patterns to deal with those failures, and we're going to talk about decoupling our systems. So distributed systems, all right? These are systems whose components are located on different computers, which communicate and coordinate their actions by passing messages to one another. Distributed systems are also really, really hard. So if anybody tells you that distributed systems are easy, they are lying to you. All right. If you know this man, Werner Vogels, the CTO of Amazon.com, he says that everything fails all the time, and he is 100% correct. So if you look at serverless applications are basically just distributed systems on steroids. That's because we have smaller, more distributed compute units, more things to think about. We have to deal with statelessness, right? So most of the functions that we're going to use are going to be stateless, which means we have to hydrate them if we're going to somehow rehydrate them. They're uncoordinated, right? So you have all these different services. They require buses or queues or pub sub-services or state machines in order for them to be able to communicate with one another. And finally, they're heavily reliant on other networked cloud services, all right? So what does it mean to be serverless? So you've heard all the definitions, things like no server management, flexible scaling, pay for value, never pay for idle, automated high availability. These are all true, but it's also a lot of configuration and knowledge of cloud services, and they're highly event-driven. So that's another thing that you need to think about when you're building serverless applications. Right, so there are a lot of services, as I mentioned. AWS breaks down services sort of as serverless. These are things like Lambda and DynamoDB and SQS. These things can scale no matter how much you throw at it. You don't have to worry about provisioning or anything like that. Then we have sort of this series of managed services. So managed services are things like Elasticsearch and Elasticache and RDS. So these things scale really, really well. We don't have to manage them, but we do need to think about provisioning them and the capacity that we need. And then you have all these things that are not serverless. So anything that runs on an EC2 instance, or things like Kubernetes and Kafka and MongoDB, all these things that are installed on VMs, these are definitely not serverless. We have to worry about managing them ourselves, and we have to worry about provisioning the capacity that we need. All right, so there's a difference between reliability and high availability. Or high availability and reliability are the same thing, but basically what it is this idea of operational performance or uptime. This is something that we used to worry about when we were maintaining services, okay, or maintaining servers. But resiliency is this different idea. This is that idea to absorb the impact of failure and still be able to provide you service with an acceptable service level, right? So that is an important thing, because it is not about preventing failure, which you're going to get. Remember, everything fails all the time. This is about how to understand and how to gracefully deal with it. All right, so the first thing we have to do is we have to think about writing code for the cloud. This is a little bit different now where we're using serverless applications. And the way that we do this is we use things like Lambda, or we use Lambda, functions as a service, for our business logic. Okay, so this is an ephemeral compute service, which means it spins up and it spins down. It's similar to containers, but obviously a little bit more efficient, a little bit faster. And it runs your code in response to events, all right? So this is not just sitting there waiting for things to happen. It will only run in response to events. It also automatically manages the runtime for you, so you don't have to worry about patching or anything like that. Also does all the scaling for you. You can control that with some concurrency. It does use a single concurrency model. So what this means is that for every concurrent connection, there's a new little container that's going to spin up to process that. So that is just something to think about in terms of where it scales and how that connects to downstream systems. And then there are no sticky sessions, no guaranteed lifespans. Lambda function could last for 30 seconds. It could last for 15 minutes. There's no guarantee that user A is going to get function X the next time they connect to it. So that can change. It's just something to keep in mind. All right, so for traditional error handling and retries, typically what we would do is we'd have a server running constantly for us, all right? So we might do something like this. We'd use a try-catch block, for example. But here's the problem. What happens to the original event if it never makes it to our Lambda function, all right? If our Lambda function never gets triggered. And then what happens if there's a network issue? So the way that CloudWatch works, CloudWatch logs, is that when it writes those CloudWatch logs, it actually is an asynchronous process. So if there's something wrong with that network, you can lose CloudWatch events. And that is possible that you lose those log files. What happens if the container crashes midway through the application? So this is something that can happen when the memory gets exceeded or something happens and the function crashes, then none of your logs are actually recorded. And then what happens if the function itself just never runs? Like let's say we get some error or something and the function just never gets triggered at all. Then what do we do with that, right? So we know that losing events is very, very, very bad. All right, so we have a couple of different function types or error types that we have to deal with to account for these different types of errors. And this is a little bit different. Obviously, we have our standard unhandled exception errors, right? So whatever, couldn't connect to the database or there's some issue, maybe a syntax error. So those things we can catch and that's fine. But what if the function times out and you never get to write your log functions at the end of it? What if it gets into this out of memory error, right? And then again, the function doesn't finish, the log files aren't written, or you get some throttling errors. And that's the situation where, there's not enough concurrency available and now you can't even trigger your Lambda function. All right. So this is something that is sort of, I like to tell people, but the cloud is better than you at doing things like error handling, at retrying failures for you, at understanding network failures, at mapping its own topology to know how to fail over and where those redundant pieces are. And again, handling failover and all that redundancy. So if the cloud is better than you at doing these things, why not let the cloud do them for you? All right. And the way that we do this is by what I call failing up the stack. And essentially is, for the most part, we do not want to catch errors and try to complete the function. In many cases, and this has a sort of depends or sometimes, but we do want to just fail the function outright. We want to return errors directly to that invoking service, right? So we do not want to swallow those errors. We want to configure all of the built-in retry mechanisms to be able to reprocess events. Now, we're going to talk about all this stuff. It gets very complicated. There are a lot of different options, but that's one thing we want to do. And we want to make sure that we utilize dead letter queues to capture events that are failed, right? So if the event never gets to our Lambda function, we have ways that we can capture those. We're going to talk about all of this. All right, so there are a couple different types of Lambda functions, or I should say 3 different types of Lambda functions. We have the Lambdalith, which we'll talk about in a minute. We have this idea of the Fat Lambda, which is an interesting approach and not necessarily a bad one. And then we have this idea of the single purpose function, which is something that we should try to strive for because this will be the most efficient and the most portable type of function that we can write. So let's talk about the Mighty Lambdalith. This is the Lambda version of the monolith from 2001 Space Odyssey. So this is when an entire application runs in one Lambda function. A Lambda function is essentially just spinning up a mini Linux server that runs for a short period of time and then shuts down. So that is possible to do. This is this sort of lift and shift approach we see when people are taking an Express app or a Flask app and they just want to move it over and have the benefits of serverless. Not necessarily a bad idea to get started. It certainly can do that. Most of the time, all of the events sent to this are going to be asynchronous via something like API Gateway or Application Load Balancer. And finally, anything that fails are going to be any partial failures are going to have to be handled in your code. So essentially what that means is that if the database can't connect or something happens where it can't do downstream, you're going to have to write some handling code in there that's going to have to catch all of those errors and account for that. And of course, there's a good possibility that you're going to lose a lot of that information because of the way that Lambda functions work. All right, so then we have the Fat Lambda, and this is when we take several methods that are sort of related to one another, and we're gonna co-locate those in a single Lambda function. Now this is usually used in order to speed up a synchronous operation. Okay, you can't really chain functions in a synchronous manner in any way that is efficient. So sometimes if we have to have a couple of synchronous things happen all in one call, then we potentially want to just put that into one Lambda function. Your partial failures are still going to be handled in the code, but it's potentially less because there's still ways that you could maybe fail the entire function. We'll talk a little bit more about that. And again, under the right circumstances, this can be very useful. I know there are several companies that do this. I have a couple of situations where I do this, where you need a synchronous response from a couple of actions. So you may have to string together a few things. It's better to put those into a single function than it is to try to connect a whole bunch of them together or have them communicate via the network. And then finally, you have the single purpose function. So this is where you have a very tightly scoped function. It handles all of your business logic for a very small case, for a discrete piece of business logic. These can be invoked both synchronously or asynchronously, so they can process events either way. The failures are generally total failures, which are great because then that way we can follow that recommendation and pass those failures back to the invoking service. And these can be reused as part of other workflows, and therefore we can scale or throttle them independently. And of course, we can apply the principle of least privilege and make sure that these things are really locked down. Okay, so let's talk about some failure modes in the cloud. I'm going to throw a lot of technical content at you, but it is important to just sort of understand that these things exist. I don't expect you to memorize them. Look at the slides later, go to the documentation, it's all in there. But the idea here is just to kind of give you an overview of what is possible and what sort of is the right approach for each different one. So first we have to talk about retries quickly. Essentially in a distributed system, retries are going to be a vital part. And most of the cloud services in AWS will guarantee at least once delivery. Now that sounds good, but that's at least once. It doesn't mean only once. So sometimes you can get the same event more than once. So what we want to try to do for that is we want to make sure that our retried events are idempotent. So we want to build in some logic or use services that provide some logic that allow us to make sure that if we submit the same event more than once, or our function receives the same event more than once, that we don't reprocess that same event, or if we do, it will have no effect on the system. All right, so what idempotent essentially means is that we can repeat that event multiple times, same result, no side effects. So things that would be idempotent would be like updating a database record. So maybe the modified date changes, but everything else is fine. We can authenticate a user 1,000 times. It shouldn't matter, shouldn't affect the state of our system. And then we can always check to see if a record is created before we actually insert a new one. Therefore, you can submit that same event over and over again. There are a whole bunch of strategies to ensure this. I am not going to go through any more of them, but definitely look it up because this is something you do need to think about. All right, so dead letter queues, want to mention these quickly. These allow you to capture those messages or those events that fail to process or are skipped. This is an important thing because sometimes messages get skipped for different reasons. We want to make sure we capture those. We can set alarms, we can inspect them, we can even replay those events if we want to. And for a lot of the services that we're going to have a situation where we're going to get failed events, SQS, SNS, and Lambda, we have the ability to add those there. All right, so there are a couple different Lambda invocation types. You have your synchronous, which is your standard request response model. That's what we're highly used to. We have an asynchronous way where we can send a message to a Lambda function and then we don't have to actually wait for it to process. It'll do that on its own after the fact. We have this idea of stream-based, which will actually push data to our Lambda functions. And then we have this polar-based system that will pull data from an SQS queue and try to run that Lambda function. Okay, so synchronous Lambda Retry Behavior is different than the other ones. Functions would be invoked directly using that request response method. The failures themselves are going to be returned right back to the invoker, which is why we want to fail the function itself. Any of those retries would have to be delegated to the application or the client that invokes them. And then some of the AWS services out there, like Alexa and Cognito, they actually automatically retry these for you. Other ones will not, though. API Gateway, ALB, step functions. If the Lambda function fails, it is up to the client to retry those. And then API Gateway and ALB actually returns those errors directly to the client so that those systems can just go ahead and retry from the client side. All All right, so asynchronous Lambda retry behavior is also different. The way that this works is there's actually a Lambda service that will accept the requests and add them to a queue. The invoker that sends, that when you send that message, it'll actually get a 202 status code and say, okay, I got the message, and then it will disconnect. So the actual event won't be processed yet, but you can disconnect and reply back to the client and say, we've safely captured that event. Now, the Lambda service has a couple different options. You can set the maximum retry attempt, so it will actually retry it up to 2 times if the event fails because of an error, which is sometimes good, right? So maybe you have some sort of throttling error, or not a throttling error, but a downstream failure. It'll retry that a couple of times. And then you can also actually use this maximum event age in seconds setting, and this will handle those throttled errors. So if you have a concurrency set on that and it can't process it because it hits up against that, it'll actually retry it for up to 6 hours, and you can set that yourself. So failed and expired events that are sent to a Lambda function asynchronously have the option to either be sent to a dead letter queue or to an on-failure destination. We'll talk a little bit about the Lambda destinations in a bit. All right, so stream-based Lambda retry behavior, the records are pushed synchronously to Lambda, either from Kinesis or DynamoDB. This happens in batches, so again, huge batches from Kinesis, somewhat smaller batches from DynamoDB. There's a maximum retry attempt, so this actually defaults to 10,000, so you're going to want to change this to something different because 10,000 is really, really high. You don't want it retrying the same failed event over and over and over again. And then you can actually set it so that if they do get stuck, it will only try a message so many times because again, these are like FIFO. This is first in, first out. So these are in order, not FIFO. So these are in order. So if a message is blocked, it'll keep retrying that batch over and over and over again. So you can set this so that it eventually would expire out if you needed it to. There's a very cool feature called bisect batch on function error, which is for poison pills. So if you do have a bad message in there, this will actually just split that batch into 2. If one of them succeeds, then fine, that gets processed. The other batch would keep getting split and split and split till it narrows down that message and is able to process the rest of it. And then all those skipped records, which we talked about, skipped records, are sent to the on-failure destination, which can either be SQS or SNS. And again, we'll talk about Lambda destinations. So for polar-based Lambda retry behavior, there's actually another service called the Lambda Polar. You don't need to know about it, but it pulls records synchronously from SQS in batches up to 10. If an error, if it fails, it actually fails the entire batch. There's no bisecting here. So you'd have to go and inspect all the messages if you do a batch. There is this maximum receive count that you can set that allows you to retry the message over and over again. That gives you the ability to, again, try it a couple of times, maybe wait for a downstream system to come back up. And then eventually, if it can't process it, it sends it into the dead letter queue. There is a polling frequency and a concurrency relationship. So if you set your concurrency a little bit lower, so maybe you set it to 50, your frequency will be adjusted based on the number of messages that are coming in and what that concurrency is. There are some rules here, and you can look these up, but essentially you have to set the visibility timeout to like 6 times your the timeout of your consuming function. This isn't well documented on the AWS documentation pages. Look it up, but this works really, really well. Okay, so Lambda destinations. So these are only for synchronous invocations right now, but essentially you can route a response or route to something on a success or a failure, or actually or a failure. So in the case of a dead letter queue on a Lambda function, you really should choose on failure or failure Lambda destinations, I should say, over standard DLQs because you'll get context information like you'll get some information about the stack trace and some of those things, which are really helpful. Destinations can either be an SQS queue, an SNS topic Lambda function, or EventBridge, which is very, very cool. And then we have destination-specific JSON format, depending on where you send them. So SQS and SNS is going to pass the JSON as a message. Lambda will pass it as the payload to the function. EventBridge will put it in the detail. And then there's sort of this weird thing where the source is Lambda with a lowercase l, even though everything else is a capital L, but that's fine. And then you'll get some detail type and some resource fields that will contain information about the function and the destination itself. So SQS has redrive policies. This only supports another SQS as a DLQ. So if you're pulling messages off of an SQS queue, once you get that maximum receive value, it'll go ahead and push it over into the DLQ for you. And then SNS has added DLQs as well. So you attach these to subscriptions, not to topics. So you could have 10 subscriptions to an SNS topic, and then you could have each one fail to a different dead letter queue or handle the dead letter queue separately. This only supports SQS queues. You can't send it back to another SNS topic. And any type of client-side errors, like if the Lambda function doesn't exist, the system won't even retry that. Messages to SQS or Lambda are actually retried up to or over 100,000 times over the course of 23 days. So those will likely never be lost. So SQS to Lambda is messages to SQS or Lambda from SNS are almost guaranteed. And then there's this other thing where SMTP or SMS and mobile is 50 retries over 6 hours, and then HTTP endpoints support their own custom-defined retry policies. So again, you can look these up, but each one of these is handled a little bit differently. EventBridge, which is a very cool service, which we'll talk a little bit about a little bit more later on. This will attempt to deliver events up to 24 hours with some sort of a back-off in place. Failed events are lost, although this is very, very unlikely just because, again, most of the services it's going to connect to are going to be other AWS services that are likely not going to be down for 24 hours. And then once the event is accepted by the target service, that's when all of those failure modes kick in. So if we send a message to Lambda from EventBridge that is sent asynchronously, the Lambda service picks that up, and then that disconnects from EventBridge, and EventBridge doesn't need to worry about that message anymore. And then the Lambda function would handle that. Like I said, Lambda functions are invoked asynchronously. All right, and then step functions. So this is another really cool service that AWS has that allows you to do state machines and orchestrate workflows. This is just a sort of an example of sort of the saga pattern that you can do and be able to work things backwards or unwind events. Lambda events in this, or Lambda in this case, are triggered synchronously, which is cool because then that way you have all these retriers and catchers within the step function service that allows you to handle all these complex error handling patterns. It gets an error name with it as well, so you can do conditional error handling. So depending on the state, you might want to do something different. You also can control those retry policies, so things like the interval seconds, backoff rate, and so forth. I'm just going to mention the AWS SDK. Built into the SDK, there are automatic retries and some sort of exponential backoff. These are just an eye chart here for a couple of different services or a couple different of the SDKs and what their timeouts and socket timeouts are and so forth. Again, whichever one you're using, you can look this information up. But there are retries built in, so you don't have to do that in your own code, which is nice. All right, let's talk about a couple of error handling patterns. We've got about 20 minutes left or so. So let's talk about caching strategies, right? So let's say we have a Lambda function that gets invoked by an API gateway. We want to query RDS. What we would do here is put a Elasticache or something in between here so that if we get a hit, we don't even have to connect to our RDS cluster. Now this is good because, again, if we have a nice warm cache, we don't even have to worry about the Lambda connections from the RDS connections from Lambda, which is helpful. If we were to get a miss, for example, then we go ahead and we contact the RDS. We do have to write this back into the Elasticache because it is not a write-through cache. We have to manage that ourselves, but then we can return the data back to the client. So a couple of key points here is we want to create an RDS connection only on misses because we are going to tie up connections to the database unless we're using something like RDS proxy that just recently went GA. We got to make sure that our TTLs are set appropriately so that our data doesn't get stale. We want to have the ability that when we write to that database that we have something that clears that cache for us. And again, you still have to size your database cluster appropriately. You're not using the cache in any way to try to mitigate the size of the cluster. What you're trying to do is just reduce the potential that if that cluster goes down, at least you'll have a little bit of a backup, be able to do that. And it takes a little bit of load off of it and reduces those connections if you are not using RDS proxy or having some connection issues. The other thing we can do is we can buffer events for throttling and durability. So if we had like a high throughput write application, and we got API gateway to Lambda. Maybe this is a webhook. We want to write data to RDS. It would be great if we could just write directly to RDS, but if RDS goes down, we're going to lose those events. So that's where we put things into an SQS queue. We can buffer those events. This is an asynchronous request so that we can just go ahead, get that ACK from the queue and says, hey, I got your message. Then we can reply back to our client and say, we're all set. We've got your message. Then we can put another Lambda function that we can throttle. And this way we set that concurrency so that we don't overwhelm that RDS cluster. And we can just pull that SQS queue. This is synchronous, so we try to write it to RDS. If everything works, we tell the queue, hey, this is great, and the messages are removed from the queue. If there is some sort of failure, then after a couple of retries or whatever our redrive policy is set to, we would just go ahead and write that to an SQS DLQ. And that gives us the ability, again, to go and look at it later. So SQS adds a tremendous amount of durability here. Those throttled Lambdas can really reduce that downstream pressure, which is great. And any failed events, like I said, are stored for further inspection and replay. This is really helpful because, again, you may have something where you have to, a downstream service is completely offline for several hours or whatever. You can just go ahead and replay those events back from that queue once that system comes back up and is running for you. Now, you don't actually need this Lambda function here when you're using API gateway. You can utilize something called service integrations, but that's just sort of an aside. The circuit breaker pattern is another very popular pattern that we can use to make sure we add resilience to our system and we can handle failures much more gracefully. So the happy path here might be that we call a Stripe API. That Stripe API replies back to us. We go back to our client. We say, hey, great, we charge your credit card. Everything is awesome. But as we know, because Werner told us, everything fails all the time. So what we have to do is figure out a way in which we can stop sending data to the Stripe API if it stops responding, or if there's some other issues that come up, throttling, things like that. So what we do is we'll put a status check here. This will actually run in our Lambda code. We'll use something like DynamoDB or Elasticache as a cache to coordinate across multiple Lambda functions. And then we'll check that and store that information and then decide whether or not the circuit is closed. If the circuit is closed, great. We make the connection to Stripe API. If that responds back to us, everything's perfect. But let's say that we get a failure from the Stripe API. What we want to do is then increment that failure count within our Lambda functions and periodically update the cache. And then once we get to a certain limit, and we can respond back to our client and tell them that that we can't connect right now. But once we get to a certain limit, then we're going to go ahead and flip a switch that says, hey, our status is open now, so our circuit is open, and we can respond back immediately to the client saying, hold on, we can't send any events to that Stripe API right now. Now, obviously, we can't do that forever, so what we want to do is periodically send what's called a half open request. If that fails, we just stay in the open state. But if it succeeds, then we update our caches, and then we can go ahead and start sending requests again because we closed our circuit. So a couple of key points here. We do want to cache our cache with warm functions, meaning that essentially we don't want to be calling that DynamoDB or Elasticache on every single invocation. We don't need to because we do want that failure count to be something reasonable. We don't want to fail after one failure, and it depends on the velocity again of whatever your throughput is. So if you got 1,000 requests per second, you might want to fail after 1,000 requests or 10,000 requests. If you've got one request per minute, then you might want to fail after 10 minutes of it not working or something like that. And again, this is something where you want to understand idempotency. The Stripe API has a great idempotent ID that you can use. Other APIs do as well, but you might want to just think about this, or you definitely want to think about this if you're calling some other API, because it is possible that you send the request and then you don't get the response. And again, in this situation too, your client could be, it doesn't have to be API gateway and a client, it could be an SQS queue processing, things like that. So you could put this pattern in a lot of different places, but this allows us to be a good citizen and make sure that we're not hammering an API that's having trouble, because that's the worst thing you can do is send more requests to an API that isn't responding or is having trouble. All right, there's this other pattern. I'm just going to go through this quickly, but this is something that EventBridge gives us the ability to do. This is this idea of a conditional retry pattern where we can get really fancy, but it's kind of a cool pattern. It works really well. We essentially send events into our processing Lambda. These are sent asynchronously. If we get a success, we send a message back to EventBridge. Those messages just go off to whatever the next, they go out to the events, whatever else is listening to that to process those next steps. If we get a failure, then what we're going to actually do is we're going to write this to a DLQ, and we can route this through EventBridge. We use a rule that's going to route any of the permanent failures. So something that is, something, what if it was a bad message or something like that. But we can actually have a replay SQS where if we just get a failed route because of there's maybe throttling or something else that happens, we can route messages to that replay SQS. And then we can use a delivery delay to use a replay Lambda that's throttled. I know this is getting kind of complicated. It's really not. That can then send an asynchronous request to the processing Lambda, and the cycle can repeat itself. Just a cool little pattern that you can use. If you want to do sort of automatic replays and some of those things. All right, so let's talk about decoupling our services. In the past, there's some legacy serverless applications out there that would use SNS as an event. As an event service itself. You send an asynchronous request, you get that ACK back as disconnected, and then that SNS topic can send messages to SQS and HTTP and email and trigger another Lambda function. So it also has now, of course, the DLQs. And this is cool because SNS is a well-defined API, right? If you think about microservices, microservice design, it does decouple those downstream processes, which is really handy. And it allows for multiple subscribers with the filters. The problem with the filters is that you have to send specific information in the message attributes to make this work. But this was a fine way to do it. A lot of applications still use this method. There is a better way now, though. We have EventBridge. EventBridge is essentially the same idea as SNS. It is for smaller events. If you're still doing like SMS or you're still doing emails or things like that, then SNS is still a better way to do it, high velocity stuff. But for just single events or small batches of events, the EventBridge works really, really well. So again, you make an asynchronous request, you get an event ID back in this situation. And then this can go to SQS and Lambda, just like SNS could, but it can also invoke step functions and event bus and like 16 others, and it integrates with SaaS products and all kinds of cool things like that. You can set all of these different rules that allow you to do different things. So a couple key points here is you can allow multiple subscribers, right? So just like SNS, and you can use much more complex rules and patterns. There's all kinds of cool things that are in there. And this allows you fine-grained control, and you can use the JSON itself. You don't have to worry about sending extra metadata in the message attributes in order to do the filtering. You can forward events to other accounts. So if you do split your microservices up by account, or you have multiple accounts for different things, you can actually communicate across those accounts. And then like we mentioned earlier, there is that 24 hours of automated retries. So the reason why this is really cool is because then you can distribute and throttle your events to your different components and implement whatever retry policies and whatever resiliency policies or patterns that we've already talked about. So this is cool because let's say we have an API gateway that triggers that Lambda function. This does something like submit an order, for example. And now this goes to our EventBridge, sends an event. We get a request back from EventBridge. We can reply back to the customer, say, hey, we got your order. This is very common when you order something from Amazon. It does not insert it directly into DynamoDB. It buffers that. Same thing when you submit a tweet for Twitter. There's all sorts of things that have a small delay in those. And that is because they are distributing these events. So what we can do then is then have services like an order service. And in this case, we'd use an SQSQ, a Lambda function, and RDS. And we can actually separate this as a completely independent service. This could be in a different account if we wanted to. And essentially that rule allows us to then route an order to that SQSQ. It hardens it there, and then we can go ahead and process off of that queue and make sure we don't overwhelm that RDS service. Let's say that we wanted to send some sort of an alert. We use Twilio in this case, right? We put another message in there or another rule, and that allows us to only have things, only pick up certain types of events and send those to our alerting service. And then maybe we have a billing service that we're going to do the Stripe thing. We get an event that comes in, again, connects to that SQSQ, disconnects. Now we can throttle that and handle things like maybe quotas or anything like that we might need to deal with. So The idea here is that these individual rules can be very specific and very detailed in terms of what they allow. So in this case, we may only want to send an alert if an event comes through as marked as order complete. We may only want to bill something if the numeric value of the total is greater than 0. Maybe we have a free ebook that we give away that we don't want to run the billing for. So this allows us to do a lot of sort of complex filtering and control at the EventBridge level, and we don't have to think about it at our individual level. Now, each one of those individual services has no idea what any other one is doing, and it doesn't need to. So some key points here is that these filters allow us to selectively trigger which services get triggered off of an event. We can manage all of that throttling and the quotas and the failures at each individual service. So all those strategies we talked about, all those different failure modes and things like that, those can be implemented for each one of these services for whatever needs to actually be done. And then again, we can use Lambda Destinations with asynchronous events. So if we were going to send something directly to a Lambda function, we have all kinds of cool things that we can do with those destinations. All right, so some key takeaways here. Be prepared for failure because everything fails all the time. Make sure you have those things in place. Utilize the built-in retry mechanisms of the cloud. They are very, very, very powerful things. They work really, really well, and they give you a lot of control over your application. Make sure you understand all these failure modes to protect against data loss. The last thing we want to do is lose an event. So think about DLQs and where that data can go if it doesn't get processed. SQs are very lightweight, very inexpensive, great place to just throw data that you can't process right away. Make sure you buffer and throttle events to distributed systems. This allows us to tweak each individual service so that it does exactly what it needs to do and only has access to what it needs. And then we can go ahead and make sure that we buffer those events and throttle them so that those can get processed when they're available. And then embrace asynchronous processes to decouple our components. There's no reason why things have to be processed immediately. That email that goes out that says your order has been processed or has been received does not need to go out immediately before that user gets a response back that says that they've submitted their order on the web. So those things can be processed later. The data that goes into Salesforce and to Marketo and to any of these other services, this can all be done after the fact. All right, and that's it. So my blog is jeremydaly.com, my podcast, serverlesschats.com, my newsletter, offbynone.io. I've got a couple of open source projects. You can check out my GitHub as well. And if you have any questions, please feel free to just contact me on Twitter, at Jeremy_Daly. Follow me. My DMs are open. I look forward to chatting with you, and thank you very much for having me.